Hello students, welcome to the session on interval estimation. Recall the difference between point estimation and interval estimation we discussed earlier. Today we will be dealing with interval estimation. In interval estimation, we say that the parameter lies in an interval, say C1, C2 with some probability.
That is, if theta is a parameter, probability of C1 less than theta less than C2 greater than or equal to 1 minus alpha for all theta in omega, the parameter space, where C1 and C2 are functions of the sample values called lower and upper bounds of the parameter. Alpha is a specified constant and 1 minus alpha is called the confidence level. The interval C1 C2 is called 100 into 1 minus alpha % confidence interval.
Alpha is a specified constant and 1 minus alpha is called the confidence level. The interval C1 C2 is called 100 into 1 minus alpha % confidence interval. Now, let us see how the confidence intervals are constructed for the estimation of the population mean, population variance, etc. But we should have an idea about the distributions of the statistics before entering into the procedure. You know that any function of sample values is a statistic. The distribution of the statistics or functions of statistics is called a sampling distribution. So, let us discuss about different types of sampling distributions. Let x1, x2, etc. xn be a random sample from a population n mu sigma square. Then x bar follows normal with mean mu and variance sigma square by n. X bar is a statistic. It means that the distribution of the sample mean x bar is again normal with mean mu and variance sigma square by n. Now, let us consider a transformation z is equal to x bar minus mu divided by sigma by root n, which follows standard normal distribution, that is normal distribution with mean 0 and variance 1. Suppose in this case the population variance sigma square is unknown, then in z is equal to x bar minus mu by sigma by root n, we replace sigma or sigma square by its unbiased estimator. S square is equal to 1 by n minus 1 summation I is equal to 1 to n xi minus x bar whole square. Therefore, we write t is equal to x bar minus mu divided by s by root n, which follows a t distribution with n minus 1 degrees of freedom. Or we can use small s is equal to 1 by n summation I is equal to 1 to n xi minus x bar whole square. Then in that case t is equal to x bar minus mu divided by s by root n minus 1. Again this follows t distribution with n minus 1 degrees of freedom. Note that when the sample size is large, t is equal to x bar minus mu by s by root n is following standard normal distribution using the central limit theorem. Similarly, we have a statistic n s square by sigma square or n minus 1 capital S square by sigma square. We call it as chi square, and chi square is equal to n minus 1 capital S square by sigma square, which follows chi-square distribution with n degrees of freedom if mu is known, or chi-square with n minus 1 degrees of freedom if mu is unknown. And we have one more statistic, F. F is equal to n1 minus 1 S1 square divided by sigma 1 square whole divided by its degrees of freedom, that is n1 minus 1, again divided by n2 minus 1 S2 square divided by sigma 2 square whole divided by n2 minus 1. This can be simplified as S1 square by S2 square into sigma 2 square divided by sigma 1 square. This statistic follows F distribution with n1 minus 1, n2 minus 1 degrees of freedom if the population parameters mu 1 and mu 2 are unknowns. Hence, we consider F is equal to S1 square by S2 square into sigma 2 square by sigma 1 square, another sampling distribution with n1 minus 1, n2 minus 1 degrees of freedom. We will consider these sampling distributions in the construction of confidence intervals. For more details like density function, mean, variance, etc. of these sampling distributions, you may refer to any text on statistics. Now, let us construct confidence interval for the population mean mu. For that, consider a random sample x1, x2, etc. xn from the normal population n mu sigma square. Assume that sigma square is known. To estimate mu, we start with an interval a comma b such that probability of a less than t of x less than b greater than or equal to 1 minus alpha. 1 minus alpha is the confidence level. Usually 1 minus alpha is taken as 90%, 95%, 99%, etc. Here we consider the statistic t of x as z is equal to x bar minus mu by sigma by root n, because sigma is known, hence the distribution of z is n01. So, to construct the confidence interval for mu, we start with probability of a less than t of x less than b greater than or equal to 1 minus alpha. It is easy to start with t of x is equal to z is equal to x bar minus mu by sigma by root n. Hence, we have probability of a less than x bar minus mu by sigma by root n less than b is greater than or equal to 1 minus alpha. Now, since the distribution of t of x is standard normal, we have for the standard normal distribution, it is a symmetric curve. So, this means that the interval a comma b contains x bar minus mu by sigma by root n with probability at least 1 minus alpha. So, here when you look at the standard normal table, we can see that probability of, if you take a as this point and b as this point, probability of A less than Z less than B is equal to 1 minus alpha. If you consider this area as 1 minus alpha, we can find out several points in the x axis such that the area between A and B is 1 minus alpha. But since the standard normal distribution is a symmetric distribution, we consider these points A and B at equal distance from the center, that is from 0. So, when you look at the standard normal table, for example, if you had to construct 95% confidence interval, probability of minus 1.96 less than Z less than 1.96 is 1 minus alpha, that is our 95%. So, this is 0.95. Hence, these 2 points minus 1.96 and 1.96 are at equal distance from 0. Similarly, if we take 90% confidence interval, you can see that so in that case this area is 0.90. In such cases, these 2 points will be minus 1.645 and plus 1.645. If you have to construct 99% confidence interval, this area is 0.99. So, in such cases, when you look at the standard normal table, you can find out that these two values as minus 2.576 and 2.576. So, generally we take these 2 points as minus Z alpha by 2 and Z alpha by 2. This is because since the total area is 1, here we are assigning the area as 1 minus alpha and the remaining area, that is alpha, is equally distributed among the left tail and the right tail. So, this area is alpha by 2 and this area is also alpha by 2. That is why it is denoted as minus Z alpha by 2 and plus Z alpha by 2. So, generally these 2 points, A, let us denote it as minus Z alpha by 2 and B as Z alpha by 2. Hence, we get probability of minus Z alpha by 2 less than x bar minus mu by sigma by root n less than Z alpha by 2 is equal to 1 minus alpha. This is because here we have equal symbol, since the area between minus Z alpha by 2 and Z alpha by 2 is equal to 1 minus alpha. Now, by adjusting the left hand side and right hand side, we can write this as probability of minus Z alpha by 2 sigma by root n less than x bar minus mu less than Z alpha by 2 sigma by root n is equal to 1 minus alpha. After rearranging the terms, we have probability of x bar minus Z alpha by 2 sigma by root n, comma x bar plus Z alpha by 2 sigma by root n is equal to 1 minus alpha. X bar minus Z alpha by 2 sigma by root n. This is equal to 1 minus alpha. Hence, the confidence interval for the parameter mu is x bar minus Z alpha by 2 sigma by root n, comma x bar plus Z alpha by 2 sigma by root n.
Confidence interval for the parameter mu when sigma is unknown and sample size n is small.
Now, we consider construction of confidence interval for population mean mu when sigma is unknown. We have the statistic T of x is equal to x bar minus mu by s by root n following T distribution with n minus 1 degrees of freedom. Then probability of A less than, again capital T of x less than B greater than or equal to 1 minus alpha. Since sigma is unknown, we use the statistic T of x is equal to x bar minus mu by s by root n. Therefore, probability of A less than x bar minus mu by capital S by root n less than B greater than or equal to 1 minus alpha. Again, T distribution is a symmetric distribution. So, when you consider the graph of the T distribution, the area between A and B is 1 minus alpha. So, the remaining area alpha is again distributed equally along the left and the right tails.
Again, when you look at the table of T distribution, if you are constructing 90% confidence interval,
that means 1 minus alpha is 0.90. So, this remaining area, that is 0.10 and half of that means this is 0.05 and this is also 0.05. But the T distribution is having degrees of freedom. So, if you are taking a random sample of 10, then the degrees of freedom of T is Tn minus 1, that means 9 degrees of freedom. So, for example, when you look at the standard normal table, you can see that probability of minus T 9 alpha by 2, that is 0.05 less than T of x less than T 9 0.05 is equal to 0.90 when these values, that is minus T 9 0.05 is minus 1.833 and this is 1.833. Similarly, if you are constructing 95% confidence interval, so this area is 95%. So, in that case alpha by 2 will be equal to 0.025 and this alpha by 2 is again 0.025. So, look at the standard look at the table of T distribution. So, there you can see that this value will be minus 2.262 and this value will be 2.262. Since it is a symmetric distribution, again we are taking A and B at equal distance from the center. Hence, generally these points are denoted as minus T n minus 1 alpha by 2 and this point is T n minus 1 alpha by 2. Hence, this becomes, this equation is probability of minus T alpha by 2 n minus 1, or we can write it as minus T n minus 1 alpha by 2 less than x bar minus mu divided by s by root n less than T n minus 1 alpha by 2 is equal to 1 minus alpha. Then after simplification we get this as, here we have minus T n minus 1 alpha by 2 into s by root n less than x bar minus mu less than T n minus 1 alpha by 2 into s by root n. Again adjusting the terms, we will get this as x bar minus T n minus 1 alpha by 2 s by root n less than mu less than x bar plus t n minus 1 alpha by 2 s by root n is equal to 1 minus alpha.
Hence, the confidence interval for the parameter mu when sigma is unknown and n small is x bar minus t n minus 1 alpha by 2 s by root n, x bar plus t n minus 1 alpha by 2 s by root n.
If you are using small s, this will become x bar minus t n minus 1 alpha by 2 small s by root n minus 1, and this is x bar plus t n minus 1 alpha by 2 small s divided by root n minus 1. If the sample size is large, again we will use instead of t x bar minus mu by s by root n, and the corresponding confidence interval you will get. Now, let us look at the construction of confidence interval for the population variance sigma square. For that, we are using this statistic chi-square is equal to n minus 1 s square by sigma square. I told you chi-square is equal to n minus 1 s square by sigma square. Is following chi-square distribution with n degrees of freedom if mu is not. That means, we are taking a random sample from the normal distribution and you have to construct confidence interval for sigma square. In that case, mu may be known or mu may be unknown. If mu is known, this will be following chi-square with n degrees of freedom. If mu is unknown, it will be following chi-square with n minus 1 degrees of freedom. So, again we will start with the interval probability of a less than n minus 1 s square by sigma square less than b greater than or equal to 1 minus alpha. For the time being, let us assume that mu is known. Now, this is following chi-square distribution. So, when you draw the graph of chi-square distribution,
in the graph of chi-square distribution, if this point is chi-square n alpha, the area to the right of this point is alpha. But we need the points a and b such that probability of a less than chi-square less than b is equal to 1 minus alpha. So, these points are denoted as chi-square n 1 minus alpha by 2 and chi-square n alpha by 2 respectively. If you are constructing 95% confidence interval, 1 minus alpha is equal to 0.95 and the areas in the left and right tails are 0.25 each. Suppose the sample size is 12, then these points are chi-square 12 0.975 and chi-square 12 0.025 respectively. Referring the chi-square table, we get chi-square 12 0.975 as 4.404 and chi-square 12 0.025 as 23.337. Therefore, probability of 4.404 less than chi-square less than 23.337 is equal to 0.95.
The place of a we write probability of chi-square n 1 minus alpha by 2 less than n minus 1 s square divided by sigma square less than chi-square n alpha by 2 is equal to 1 minus alpha. We are searching for the confidence interval for sigma square. So, by adjusting the terms, we get probability of, we can write it as 1 by chi-square, taking the reciprocal, the inequality will change. So, chi-square n alpha by 2 less than sigma square by n minus 1 s square less than 1 by chi-square n 1 minus alpha by 2. This is equal to 1 minus alpha, and hence probability of n minus 1 s square by chi square n alpha by 2 less than sigma square less than n minus 1 s square divided by chi square n 1 minus alpha by 2 is equal to 1 minus alpha. And hence the confidence interval for sigma square when mu is known is n minus 1 s square divided by chi square n alpha by 2 n minus 1 capital S square divided by chi square n 1 minus alpha by 2. So, this is the 1 minus alpha percent or 100 into 1 minus alpha percent confidence interval for the parameter sigma square. When mu is unknown, you know that this will be following chi square with n minus 1 degrees of freedom. So, the corresponding confidence interval will be n minus 1 s square by chi square n minus 1 alpha by 2 and n minus 1 s square chi square n minus 1 1 minus alpha by 2. Next, we consider the construction of confidence interval for ratio of variances. So, in the case of ratio of variances, we use the statistic f is equal to s1 square by s2 square sigma 2 square by sigma 1 square, which is following f n1 minus 1 n2 minus 1. Then probability of a less than f, that is s1 square by s2 square sigma 2 square by sigma 1 square less than b greater than or equal to 1 minus alpha. So, when you look at the table for f distribution, you will get the value of a as f 1 minus alpha by 2, degrees of freedom n1 minus 1 n2 minus 1 less than s1 square by s2 square sigma 2 square by sigma 1 square less than f alpha by 2 is equal to 1 minus alpha. And hence, by taking the reciprocal 1 by f alpha by 2 less than s2 square sigma 1 square by s1 square sigma 2 square less than 1 by f 1 minus alpha by 2 is equal to 1 minus alpha. Therefore, probability of s1 square f alpha by 2 divided by s2 square s1 square by s2 square f alpha by 2 less than sigma 1 square by sigma 2 square less than s1 square by s2 square 1 by f 1 minus alpha by 2 is equal to 1 minus alpha. And hence, the confidence interval for the ratio of variances is s1 square by, this is not s1, this is s2 square, s1 square by s2 square f alpha by 2 and s1 square by s2 square 1 by f 1 minus alpha by 2. As an illustration, I shall work out a question. A sample of size 20 from a normal population has a mean of 65 and variance 60. Construct 95% confidence interval for the population mean. Here we can see that the population variance is unknown. Hence, the confidence interval we have constructed is x bar minus t n minus 1 alpha by 2 s by root n x bar plus t n minus 1 alpha by 2 s by root n. Substituting the values, we get here we have x bar is equal to 65 and s square is equal to 60, sample variance is 60. We are taking random sample of size 20. So, t 19, we are constructing 95% confidence interval. So, T19 0.025 from this table of T distribution we will get it as 2.09. So, substituting in the confidence interval you will get the value as 61.38, 68.62 as the confidence interval for the population mean mu. You can do more problems for better understanding, and now I conclude this session. Thank you.